Pressures are used in lot of machineries that we operate, and these machineries are based on the principle of hydraulic force multiplier. Consider two cylinders connected in carrying a fluid. On one cylinder, there is a piston of area A1. In the other one, there is a piston of area A2. If we apply additional force F1 on this piston, this will create an additional pressure F1 by A1 in the fluid. This additional pressure would be transmitted everywhere within the fluid. So this same additional pressure F1 over A1 would appear at all points, even at the face of the second piston. And so the force developed in the second piston would be F2 is equal to F1 divided by A1 multiplied by A2. And if A2 is large compared to A1, force F2 would be large. This is the principle of force multiplier, which is used in various devices. Shown here is a fancy pneumatic lift. This lift is nothing but a cylinder within which a capsule carrying the passengers travel. This cylinder is connected to the inlet and outlet port of a air pump, a compressor, would then press the capsule down, and the capsule carrying the passengers would come down. But if we connect the output to the input of the compressor, then it will suck air out from the top and it will decrease the pressure below the atmospheric pressure. The atmospheric pressure is acting below the capsule, and so the pressure difference multiplied by the large area of the capsule results in a large force that carries the capsule up. This picture shows a pressure actuator used in all kinds of hydraulic machinery. What it does is that a fluid at a large pressure is pumped into it, and as it pumps, this acts on this piston, and this piston moves in that direction, applying a force in whatever equipment that we want to apply force at. Example of this is this earth mover. This is a pressure actuator. Applying hydraulic pressures at this end would extend this rod and would make this arm turn in that direction. We can apply very large forces through these actuators. These actuators are also used in controlling the control surfaces of an aircraft. This hydraulic table for lifting loads also uses two actuators in a similar manner. Let's now consider forces and pressure in fluids which are moving as a rigid body. Let's consider a container which is accelerating in the horizontal direction. Consider a horizontal fluid element of cross-sectional area dA. Then the net force on this fluid element in the horizontal direction is P1 dA, where P1 is the pressure on the left face, minus P2 dA, where P2 is the pressure on the right face. And this should be equal to the mass of the fluid element times the acceleration. But the pressure in the fluids depend upon the depth from the free surface. If the fluid is accelerating the horizontal direction, the fluid pressure variation in the vertical direction would not change. So the pressure at this point would be the atmospheric pressure plus rho gh. If the fluid is accelerating, P1 must be greater than P2. So pressure P1 must be greater than P2. So the depth of this phase from the free surface should be more than the depth of this phase from the free surface. This means the free surface cannot be horizontal. The depth have to be different. More above point 1 and less above point 2. Here we have shown this. The depth is h1 above point 1 and h2 above point 2. Clearly, dm, the mass of the fluid element, would be the density rho times dx, the length of the fluid element, times the cross-sectional area dA. Acceleration A, if I plug in this for dm, I get a simplified equation: dh by dx is A by g. dh by dx is the slope of this line, is A by g. Acceleration divided by the gravity. Next, we consider a rotating container, a container of a liquid in which is rotating about its axis at an angular speed omega. We see that the free surface of this is curved. If this was a level at rest, then when it is rotating at omega, this becomes, the curved line becomes the free surface. Again, we consider this small element shown as white at the radius r from the axis. Consider the force balance. At the left face of this white element, the pressure is rho gh multiplied by dA. The pressure at the right face is rho g h plus dh by Taylor's expansion multiplied by the area, which is twice by r dz, and this should be equal to mass times the acceleration. And acceleration is the centripetal acceleration r omega square. And so on simplifying this, we get dh is equal to omega square by g r dr. And so by integrating this and using that at r is equal to 0, the depth is h r0, we get this equation for the free surface. This clearly is parabolic. Here I have calculated the free surface for various values omega. The horizontal line is for 0 speed, and as omega increases, At the center, the free surface dips, and near the wall, it climbs up.
When only gravity is at play, liquid surfaces in the laboratory are flat and horizontal. However, when we spin this container of water, it rotates as a solid body, and centrifugal acceleration distorts the free surface into a parabolic shape. An accompanying CFD simulation shows colored pressure contours, revealing that the pressure indeed rises linearly downward from any point on the surface, just like the case for a motionless body of water, according to the principle of hydrostatic pressure.